All right, welcome. In today's discussion, we are going to introduce you to wind power. Essentially, we'll talk a little bit about where does the wind come from. Then we'll move into how do we characterize or measure how that wind is available, because there's a lot of mapping data that's available, and maybe for your house, for a fairly low cost installation, you may be willing to do that. But for a longer term one, the projections that we have, all the maps we have are just projections, and so we have to be pretty careful about just using the wind resource map. And then we'll characterize and essentially convert that energy from the wind into some sort of energy that is able to move some sort of actual mass, right? And if you think about it, a good example is how a sail, right? How the sail transfers the wind energy into movement of a sailboat, for example. Excuse me. So, where does the wind come from? As we discussed earlier in the semester, almost all renewable energy that you find comes from the sun, and wind is one of those. The primary source is convection cooling and heating. So depending on how the Earth, the solar radiation impacts upon the Earth, will determine effectiveness of heating up a local area or at cooling. And the effect of that actually will cause winds. So a perfect example is the equator, right? The equator has, land and water and whatnot, and so it's a fairly dark object, relatively speaking. If you look at its what's called its not its color ending index, but its temperature that it emits radiation to mimic it, it's got a fairly low temperature. Whereas opposed to the North and South Pole, right? When we think about the North and South Pole, those have do a very good job of reflecting any energy that's stored, if they get any sunlight at all. So what ends up happening is you have more heating at the equator and cooling at the poles. And so just because of the pressure densities and the differences in pressure of the oxygen or the air that's in between those two locations, you're going to get wind primarily flowing because of pressure densities. And so the wind that we're talking about, you always see a wind flow because of a change in the density, all right? So obviously the wind flow or wind direction is going to be from a higher pressure to a lower pressure. So we can figure out directions there. That's why when we think about being in North America, the wind tends to flow from west to east, and that has a lot to do with the fact with the Earth's rotation as well as affecting that heating. But we have some storms where that can change, and again, it's all primarily due to the heating effects of what the solar radiation does. So that's essentially where the wind comes from. That's the prevailing wind direction. Locally, though, many other things can influence it. Here's a more detailed one, and you can see just sort of in a specific geographic area, you have the solar radiation impinging upon a mountain or a hill, for example, and then that solar radiation is going to heat the ground, which then is going to heat the surrounding atmosphere. And then it's going to warm the air up, and then that's going to decrease the density of the air mass that's there. That's going to rise, and then the cooler air that's further away from the surface is going to be cooler, right? And if you don't agree with that, think about when you're in the jet stream, if you're at a plane at 35,000 feet, why is the atmosphere at that elevation so much cooler than it is down at the ground? It's because of the solar radiation. The sun's energy is absorbed into the ground, and then that heats up the surrounding area. And the further away you are from the ground, the less effective the sun's radiation is at heating that area, that mass. There is some heating, but it's pretty minimal. Most of the heating that occurs is because of the ground. So that shows you the first slide here, or the first image here, shows you in a location, but you also can see the difference. Let me change the color here. In the effect of being offshore. So again, the air around the ground is going to have a different heating effect than on the ocean. There's a couple things happening, right? So if you think about the ocean, you think about its color versus how light it is compared to the ground. It tends to be a little bit lighter, unless obviously you're in a bright sandy beach or something like that. But the land mass tends to be darker. Think about green shrubbery and whatnot. That's a much darker color than the blue that you'd see in the ocean. The other thing that impacts that is the ocean's always moving, right? Where hopefully the ground is not moving. So the idea there that the ocean, as it gets hotter, that material will change because there's wave action happening, there's some heating and cooling inside the ocean. So the ocean itself is a pretty moderate temperature. You don't have huge changes in temperature. It's just a massive heat sink essentially. So that's why you think about the ocean being, a certain temperature, and it doesn't vary all that much within an area. Obviously, you get closer and closer to warmer climates, the water temperature goes up, but relatively speaking, the warmest temperature probably is in the low 80s, and the coolest temperature, if you go way up north, could be perhaps in the low 30s, but you're talking about a temperature difference of 50 degrees, where if you think about over land, you can have a high temperature of 110, 120 degrees, and a minus 50, minus 60 degrees, so much greater temperature differences over land. It exacerbates a little bit at night, mainly because if you think about at night, there's no more solar radiation occurring. So now you have all that heat that's being rejected from the land that is actually warming that area. And then there's none that's being replaced, so your body will cool off rapidly, or the land will cool off rapidly, and then you'll have less heating effect. So it could be residual depending on how hot it's been or how much solar radiation you've received. If it's been a bright sunny day for many, many days in a row, the Earth has stored up a massive amount of heat, and so it's going to take a while for it to reject that heat in the atmosphere. And sometimes you can get a change in circulation because now the warmer air could be, well, it always will be above, but the temperature difference will be different, so you actually can get circulation going in a different direction. And similarly in the ocean, right? There are points in time at night when the ocean temperature is actually higher than the ground temperature, so you can get circulation in an opposite direction for that. Globally, we can look at global wind patterns, and this is actually looking at it sort of over Europe, and you can actually see some of the pressure changes and some general patterns of flowing. So you have, hard to see here, but you can see some of the pressure levels. And we go from a higher to a low pressure, so the prevailing wind direction would be in that location. And then because you have two high pressure areas here, it's going to funnel that into those areas, okay? So it's going to force the wind to either go in this direction or in this direction, but it can't go in that direction because you can see that it's got a higher pressure behind. So just by looking at pressure maps, if you have an ability to measure the pressure of the atmosphere, you can have a pretty good prediction of what location and what direction the wind's going to go. So when you see the weather forecast and they talk about a northeasterly wind, they can predict it based on knowing what the pressures are. That's like day ahead type stuff. If you're a week ahead, then you're basing it on some weather projections and models, and those can be less accurate. Oops. Here it sort of gives you more detail, and so you can see the higher pressure, and so you're circulating out away from the higher pressure, and then you circulate in towards the lower pressure. So it's not a uniform direction. You can see you can get some circulation, and mainly the circulation is because of the two pressure systems that are located in close proximity, or relatively close proximity to each other. So you'll sort of circulate on in that direction. And obviously, it could be counterclockwise or clockwise, depending upon the Earth's rotation. So, the old thing about what happens in South America, or the southern hemisphere versus northern hemisphere, when you flush your toilet and you see the water direction goes down, why is it different in the southern hemisphere than the northern hemisphere? Well, it's because of the relative, the direction is the same, but if you look at it from a different perspective of where you are north and south, the water direction is different. So that's the same thing that you see what's going on here. All right, so now we have a little bit of information, and again, this is not a meteorological course, so we're not going to get into a lot of the modeling of that. There is a great amount of effort done to come up with pretty accurate models. We're going to assume that the wind maps that we have are pretty accurate, or we can get some very specific data at particular locations. What's more interesting to us is we would like to figure out, where do we put our wind turbines to collect energy? Where do we site them? So what we do, or what's been generalized, is depending on the elevation. So the wind at 10 meters versus 50 meters is going to look very different, right? Close to the surface, the Earth's surface is considered rough, right? Like sandpaper to the wind. So it's going to tend to want to slow down the wind. Whereas you get in higher elevation, it's not as rough, right? It's smoother. If you think about landmass, how tall are trees? 100 feet tall. Mountains, hills, whatever. Those can have some effects on it. Buildings, right? 50 meters is approximately 180 feet or so, 170 something feet. So that's not a particularly tall structure, so that is going to tend to slow the wind down. Whereas if you're offshore, right, going from 10 meters to 50 meters is not going to be that much because the water, there's not a lot of things to slow the wind down. So when you think about offshore versus onshore, you have to get much higher elevations to get away from the effect of the slowing of the wind because of the Earth's surface than you do over water because you have wave heights, and that's essentially all that's going to slow the wind down. So your turbine heights can be much, much lower offshore to get to those power levels that you're talking about. First off, the wind tends to be more higher speeds offshore, but that has a lot to do with the fact that there's less friction for the wind. So I'll use that term, and it's not 100% accurate to say friction, but it works pretty well. So these are the 7 different classes of wind power that we talk about. And at 10 meters, if you want to be in class 7, you need to be able to have a power density. So everything's going to be power density, or mostly everything in this class is power density, which is how many watts per square meter you can get. So if the wind is blowing at between 7 and 9.4 meters per second, then you're going to have anywhere from 4 to 1,000 watts per square meter, okay? Which, if you think about 7 to 9.4, 10 meters per second wind is 33, 34 mile an hour winds. That's clipping along pretty good. So you can feel, there's a fair amount of power in the wind at those speeds. But because the wind speed is so much higher, because again, there's less influence from the Earth's surface, that same class has to have a much higher power density at 50 meters than it does at 10 meters. So to be considered class 7 winds at 50 meters above the elevation that you're at, you need to have 8.8 to almost 12 meters per second of wind. One thing I would like you to note, you'll notice here to go from 1,000 to 2,000, I only have to go up by 2.5 meters, right, per second, as opposed to going from 4 to 8, right, which is a 400 meter increase. A 400 watt increase. I went up from 7.0 to 8.8, so that's 1.8 meters. So this is a 1.8 meters per second increase to give me 400 watts. This here, to go from here to here, you'll notice is a 1,000 meter increase, but how I did that was I used 2.5 meters per second. So what you're starting to see, perhaps, is a nonlinear relationship between wind speed and power density in the wind, okay? So that's an important characteristic to understand and note because that is something that we need to figure out. It is not a linear aspect. But wind power density is going to be the same thing as photovoltaic. You're going to do things in watts per square meter. And if you were to look at what we would typically experience for sun, if we could capture peak sun on the Earth's surface, we would get about 1,000 watts per square meter for the sun, okay? So to get to that same level of power from the wind, you need to be riding at about 9.4 meters per second. Whereas as long as the sun's bright and shining, then, we're good to go, right? So you can start to see how solar has some advantages because with peak sun, you get 1,000 watts. With wind, you need 9.4 meters per second, which is a pretty stiff wind that is not, where a lot of people have it. And keep in mind, this class is renewable energy as it relates to integrating into the grid. So sure, I can have, 10 meter per second wind all day, but if there's no population nearby, that doesn't do me any good, right? It has to be relatively close to some population centers. You don't want the wind resource to be really strong 1,000 miles away because that is not going to be a great opportunity for us to integrate it into our grid. Question? Okay, that's fine. If you come back, just another question?
Yeah, but isn't it also true that solar panels only collect energy at 20% efficiency?
So the
I would only get 200 watts per square meter.
So the question is, or the comment is, doesn't solar collect only about 20% of the energy that is on the face? And the answer is current technology can maybe get 22, 24, but you're assuming that the wind collects 100%, which it does not. We'll look at maximum theoretical efficiencies of about 60%, but in reality, most wind turbines are about 40 to 44, 45%. So that's why you've seen a lot more commercial stuff, because up until recently, you had PV arrays getting 10% efficient, right? Really low. And wind turbines, not without that much effort, can be at 44, 45%. So seen a lot more. But as you start to get multi-junction, better technologies figuring out, you're getting higher and higher levels of efficiency. So maybe with 22, 24, 25%, and you can take a look at that and go from there. So, but yeah, probably about double the best case efficiency for PV. But putting up a wind turbine is a pretty expensive endeavor. So there's some trade-offs associated with it, and we'll discuss those as we go through. So here is more data with classes of wind at 30 meters and 50 meters. And you can take a look and you can recognize the color classes. So the darker blue is the higher wind speeds, the lighter colors, the white. Yes, sir?
Weird question. It seems strange to me that the power density of the sun is like 1,100 watts per square meter.
It's about 1,000 watts per square meter, yep. That's under peak sun.
Right, but the wind power density can be greater than that when, as you talked about, it's the convection interaction between the
Yep.
ground that heats the wind. Is that just due to it's more concentrated in some areas and it dissipates in other areas? How are you getting a higher power density from wind than from sun?
Right, so the question is, how do you get a higher power density from wind than the sun? So the idea is that the sun is putting out fairly uniform over a certain area, a very large area, and the sun is just putting it out about 1,000 watts per meter squared. With the wind, it's more of a concentrating effect because, again, that surface area is being heated, which is then heating the air, and then depending on the Earth's rotation and the topography, that wind from that heat gets concentrated into smaller areas. So that heating that you get, 1,000 watts, could be over a 50-mile, 1,000-mile square mile area, but where the wind is, that might be funneling to 5, 10, maybe 20 miles in width. So all that heating is being concentrated because of the topography of the Earth. So that's the reason why. If the Earth was perfectly flat, smooth surface, you wouldn't see any of that. It would basically be the same. You probably wouldn't have any heating from that, so yeah. That's exactly the reason why, is because of the concentration. And that brings up a really good job, because if I have peak sun, right, everywhere in the US, it's going to be about 1,000 watts under peak sun conditions. So this map would be one color. It is not one color for wind, right? And that has a lot to do with topography, jet stream, elevation, right? In the middle of the country, we have higher elevations. Some heating and cooling, right? So we have oceans at 50-something degrees here and here, right? And then the land, we have some land mass that continues on here. So you would tend to have some concentrating wind that interacts in that location. So these colors here, right in the center of the country, is where you have the best wind resource, okay? Where would you have the best solar resource if you took it on an average over the course of a day? Down here. Higher elevations, right? Not a lot of bad weather there. It tends to be bright and sunny, 310, 320 days of bright sunshine a year. Again, that's influenced by the topography and a few other things. But very different in terms of what's happening, okay? But good question. So this is the map that shows you sort of where the wind resources are. Up in New England, we have okay wind, but again, this is kind of zoomed out quite a bit, so you don't get to see the specific highlighted areas. But you can see in Maine, we've got a little bit of lighter green, so we're getting into the higher wind elevations, so 5, 5.5, you would generally want to be at least 6 meters per second before you'd even consider putting in a commercial scale wind farm. But in the middle of the country, right, when we think of locations that don't really tend to focus on renewables, for example, Texas, right? When you think of Texas, what do you think of? Oil, right? Oil is the biggest thing. If you go up into the Panhandle, up in North Texas or Northern Texas, depending on who you ask, there's tremendous number of wind turbines that are located there. Texas is actually the largest producer of wind energy in the country. And you think of Texas as oil? Yes, it does a lot of oil too, but it does anything based on, can I make a profit on this? Kansas does a lot. So any of these middle states, Oklahoma, they would have lots of wind resources. So that's where you get it. So even though you don't necessarily think of those places as being good for wind or good from an environmental perspective, or maybe they're public policies, if somebody wants to put a wind farm in and they can make money, the government's not going to say no. There's going to be opportunities. If you look down in the southeastern part of the United States, very, very poor wind resources. Poor. So you don't see wind turbines in those locations or wind farms. If you plotted the slides this morning, I apologize. I just updated the slides maybe an hour ago. Tried to include some information about offshore wind, because offshore wind has a lot of opportunities. And I just zoomed in specifically to New England and picked up a little bit of New York. And you'll notice here, right, don't have to get too far offshore, and you're getting 9.5 to 10 meters per second, which would be considered class 7 winds. And that's at 90 meters, which is not all that tall. Sounds like it, but it really isn't. So if you look at the legend, and let me see if I can move this up just a little bit. This right here shows you 50 miles. So off here is just a sliver off the coast of Maine, and you're getting, class 7 winds. Pretty much all along the New England up until you start getting past Massachusetts. Rhode Island is when the wind speed picks up. So that's why you're seeing a lot of interest in offshore wind, because you have massive populations near the coastline and really, really good wind resources that are in close proximity, right? From Augusta to Bangor, if you did by the crow flies, that's probably 60 to 70 miles. Again, as the crow flies, don't go by the exit numbers, go by as the crow flies. But you can see that's 50 miles to go there. That's not a far distance. From a transmission line perspective, 50 miles is not that long at all. So if you can figure out where to locate these wind turbines offshore, you wouldn't see them. So I think about 7 miles off the coast, you can't even see because of the horizon. It's just beyond the horizon, so you don't even have an issue with that. The problem becomes is the commercial fisher, I don't know what the term, fisher people, I don't know if that's the gender neutral term, so I'm not trying to make fun of it, I just don't know. Commercial fisher folks, how's that? We'll go with that, that's non-gender specific. They may not want to have wind turbines because that impacts their ability to fish. So, there has to be some stuff that's there. But, massive wind resources. I also included this because I would encourage you to go check this out. If you go to nrel.gov, this is a renewable energy class, so spending some time at the National Renewable Energy Lab website is a pretty good thing to do. And you can actually have this software called Prospector that brings you specific maps of where you want to go. And you can look at offshore, onshore, different elevations. It has that information available to you. So I just said, well, can I get a better map for some offshore stuff? Because usually they tend to be a little bit odd. And you can see this took me 5 minutes with a legend and a distance to come up with that. And so, again, I would take a look at this Prospector website because it gives you a pretty good idea. This is fairly new. This has only been available for the last year or so. Here's over the world. And again, we only include it to sort of show you how, at the poles, not much happening at the North and South Pole for wind resource. Not a lot of heating there, and the Earth's rotation really doesn't have the same level of influence. Whereas if you look, over land, it's not great. But if you look, offshore, great opportunities. And you get this little funneling effect right off the coast of Europe that you get really good wind resources, pretty stable wind resources that go there, okay? So the darker the blue, the better the wind resources that you can experience. Europe is sort of leading the pack at this point in terms of renewables. So if you're not exactly sure, topography-wise, you can see France, Italy, UK, and Netherlands, Denmark, Germany. I mean, you just kind of piecemeal your map from there. And again, the closer to purple you are, the higher the wind resource, okay? So if you look at the UK, pretty good wind resources that are all along there. So their difference is they just don't have the land mass necessarily available to support a lot of wind farms because it takes up a lot of room and it's hard to have a farm or population under a wind turbine. There are some impacts to humans and livestock and whatever if you have wind farms that are there. So things to think about in terms of where you site these. We're offshore, not as much of a big deal. This is the most accurate map that I can still find for specific to being in the state of Maine. So I had that previous slide that showed you all of the US. Now this is very specific and zoomed in into the state of Maine. And if you think about where the wind farms are located, you have a number of them up in this area here. So up in the Presque Isle area, there's Mars Hill in that area. There's also a few in Lincoln. So Lincoln is, approximately in this area. So reasonably good, 5 to 6. There's one pretty close to Orono, Passadumkeag, but it follows a ridge, right? So it follows along a ridge. And then you have a number of them over here in western Maine that have pretty good wind resources. And so those actually show not all the details, but once you start getting in higher elevations, so if you're at the top of Mars Hill, which maybe is 3,000 feet, well, you don't have a lot of the Earth surface around you to impact or affect the wind that experiences. And so if you run those wind turbines along the ridge line, which they are in Mars Hill, you actually get pretty good wind resource. The downside is you can see them for a long distance because they're at the top of the ridge. So it just depends on, do you perceive wind farms or wind turbines to be pretty or ugly? Denmark is one of the leaders or the pioneers in terms of wind resource development. So understanding or having some of the information, they've done a tremendous amount of work. And so usually you can actually find way more information for Denmark. And so this is a map and you can see it's all in Danish. This is the best information. But it shows you power levels, the colors, and then it also shows you some of their transmission. So if you were to zoom in, you could actually see, some of the transmission of their systems in there and some roadways. So sort of showing you where the opportunities are, and then you can actually look at some of the distributions, wind speeds, as well as some growth in wind. So pretty good information that's there. So I keep talking about sandpaper effect, right? How smooth the Earth's surface is to wind. Well, that's an important characteristic because if we have a particular site, and let's just say that we're located in the middle of a very large field that's been, a hay field that's been that way for many, many years, and you run a wind resource measurement and then you get a certain wind speed. Well, how's that going to compare if you're into, let's say, the city of Bangor with, hills and valleys and towns, buildings around it, 4, 5, 6-story buildings. You're going to get a different reading at 50 meters from Bangor than you will in the middle of a field. What I mean by that is the higher you go in elevation away from the city in Bangor, the faster the wind speed should be as compared to being out in the middle of a field because the surface around that field tends to be slipperier to wind than it does to Bangor. And so we talk about that as being how rough is the area around a particular site or a proposed site to wind. So water, right? You're going to have a pretty low roughness coefficient for the surrounding area. If you're in New York City, you're going to have a very high roughness coefficient. So we just use a pretty simple equation where if we have a velocity of the wind at a specific height, so we know the velocity at some height, that's V0 and H0. we can estimate what the velocity is going to be at another height, a higher height, by using this equation. So if you have data at 30 meters and you want to project it at 60 meters, you can use this equation to predict what the velocity will be at 60 meters as long as you know what this friction coefficient is, that term alpha. Okay? So alpha is going to range between 0.4 and 0.1. There's nothing that's perfectly smooth, right, or stays perfectly smooth, so it's never going to be 0. So it's going to be, approximately a low value. In Europe, they use a slightly different formulation. They use this ln of h over z, and so z is our roughness length. They do it in terms of a length. So you get similar results, but not accurate. If you want super duper accurate, the best thing to use is what's called an anemometer tower. Anemometer is another way to say a speedometer for the wind. That's all it is. Okay? And here's some typical roughness lengths. So we have more data for roughness lengths than our friction coefficient. So at C, very low roughness length, right? Once we start moving in, big city centers, our roughness length can get all the way to 2. So essentially what that tells you is, again, if I have data in a city and I want to predict what the wind resource is going to be at another 30 meters above my wind data, then it's going to have, that 30-meter height difference is going to have almost negligible effect out to sea. So when I talked about if you're 80 meters versus 100 meters out to sea, the wind speed is going to be change is going to be almost negligible. But if you're in a city, a big city, you're going to see a big change in the wind speed within reason. Obviously, if you're taking a measurement above any skyscrapers or tall hills nearby, you're not going to get a huge change between the two. So you would go with that. And this just sort of shows you as I increase my alpha. So this is the C. This is when we're getting closer to a city. Our ratio gets better. So essentially what this tells me is I'm not going to see much of a change in my velocity at a certain height as compared to if I'm in the middle of the city. So I'm getting a huge change. I'm getting a doubling of speed for every increase in height. All right? And then correspondingly, how does the power change? How does the power in the wind change? Well, because my velocity is not changing much, I don't get a huge power change when it's a pretty slippery area to the wind. When it's a pretty rough area to the wind, I'm going to get a huge change in power. And this curve, you can see, blows out of here because, again, we have that nonlinear characteristic between the wind speed and the power, right? If it was linear, these curves would essentially look the same, but it is not linear, so this goes up pretty dramatically pretty quickly. Here's an anemometer setup, and it's really fascinating. I actually was lucky enough to be involved in the erection of one of these towers. So the towers can get to be 300 feet in height, so depending on where you are, you can actually go 300 feet. And it's literally a tilt-up tower, so it's erected on the ground, so they take these 6 or 8 foot cylinders and they just kind of stack them on top of each other, and then they mount these, arms, and you want to get these arms well away from the tower because the tower itself will influence the measurements, right? It's going to slow the wind down, and it's a solid cylindrical a piece of pipe essentially that is tilted up. So you want to be a certain distance away. And you literally use the guy wires to help you start to tilt up the tower. And then you have 3 sets of guys are located 120 degrees apart, and then you have multiple locations. And literally the way that you straighten the tower up, because when it goes up it looks like a snake, it's all crooked, and so you literally will have a person tighten this location on this guy wire, loosen it over here, and it's just like a puzzle to figure out how to get the tower straight, but it only takes a few hours with a good crew to get it erected. You want to make sure your anemometers are in this prevailing wind direction, and the reason being is because I don't want anything to impact my measurement. If the prevailing wind direction was this side, well, it would hit the tower first, slow down, before it would come around, so you wouldn't get an accurate measurement, okay? You will notice 3 levels of anemometer. Well, if I know the wind speed here, we'll call it V1, V2, V3, and I know the height difference between these two, I can calculate what my Z or my alpha are equal to at a specific location. So let's say that 300-foot tower wasn't tall enough. Maybe I want to get to 400 feet. I can predict what that height's going to be just by, or that speed's going to be just by using the coefficients that I calculated from here. Okay? This also shows you a couple of wind directions, right? So did I get the prevailing wind direction correctly? Because locating the tower, as we learn, or locating the wind farm, it's important to try to face the turbines in the prevailing wind direction. The larger commercial ones will auto adjust to be in line with each other, but if you have more than one turbine, you want to make sure that they're spaced in a way to minimize the impact on the farm based on its location. You have a data logger here that's recording all this information, and the last little sort of important thing, well, I guess not last, because you have a lightning arrestor, not a lightning arrestor, but a lightning device that actually is designed to take the hit. So if there's lightning in the area, let the conductor take the hit. As long as it's not too hard of a hit, it can take the lightning hit. It's only for a very brief amount of time, so it's the tallest thing around. It takes the hit, it directs the energy down to ground, and then no big deal. Nothing blows up. I mean, these are designed to take care of that all the time. No big deal. But another important thing is the little device over there. That measures temperature. Why do you think temperature is important? You can pretty accurately predict what the temperature is going to be at a particular location because it does affect the density of the air. So the lower the temperature, the higher the density, so you can get improvements in power. Why would you want to know what the temperature is? Well, it's really for data checking. Oh, you have a question, comment, or?
I was just going to say, like we were talking about before, it's the radiation from the Earth to the wind.
It would seem like that, but so the comment was is it's effectively from the radiation, from the solar radiation and the capturing of energy or heat, and then how that affects the environment around there. It actually has more to do with data checking. What if you have, so this records the data every 10 minutes, and it takes there's a lot of data. It's a tremendous amount of statistical analysis to make sure that it's correct. So if you have a bunch of data that says 0 meters per second, but the wind speed, the wind direction has been changing, so should be indicating that, but there's not been any movement for speed, and the temperature is below 32 degrees, or 0 degrees Celsius. These things are constantly spinning. If they get ice on them, they could lock up. So it's really just for data checking. If your temperature is below that, if this thing has been moving a little bit and wiggling, I guess those are less susceptible or less sensitive to icing. So you actually have to throw that data away. So it's really just for data checking. That's why you have an accurate temperature indicator. It's nothing else than just, is my data good or not? Because you'll be collecting data for 2 years, if you can, even longer. But collecting data for 2 years, you're storing a bunch of data every 10 minutes for 2 years. That's a tremendous amount of data. And the fact is you're going to have a bunch of bad data. So there's a lot of testing that you need to do, chi-square tests, t-tests. I mean, I'm not a statistician, but there's a massive amount of data that needs to get done. And then when you're done, you kick out a couple of plots. You kick out something that it gives you diurnal wind speed, which is based on the time of day, average, and then prevailing wind direction. That's called a wind rose. I guess it looks like a flower, so they call it a wind rose. And so you can see this, would be most likely the prevailing wind direction that you would experience. And then the highest average wind speed over the course of time, right about here. So 7 meters per second at about 14 hours, 2 o'clock in the afternoon. So then we take the data that has broken down by diurnal and peak, and then we're going to kind of do that, not on an average, but we're going to reconfigure that to be based on what is the wind speed what is a certain wind speed, and for how many hours is it at that particular wind speed. And so we're going to set up a distribution. So this is like a probability distribution, but we're going to do it with actual data, right? So if we can get an anemometer tower and actually get data, then we can say, well, we got no wind speed for 24 hours, or between 0 and, let's say, 0.5, 0.6 meters per second. From 0.5 to 1.5, we had this many hours, and on and on and on until we get to the point where, you know, you're outside any realistic 25 meters per second wind is, you know, that's essentially hurricane winds, and your wind turbines probably wouldn't be running. So you can actually create this distribution, and it doesn't look like a normal distribution, does it? If it is, I have to regrade all my tests and think about how to do things. But it's skewed, right? It's skewed to the left, so we can't characterize that as a normal distribution. We'll have to come up with a different distribution. But let's just do it with the brute force method. Let's just say we want to calculate a mean speed, a mean wind speed. So we take the number of hours in a year, 8762. We'll just call it 8760 to make it easy. And then we're going to sum the number of hours that a particular wind speed existed just by looking at that point. And then we're going to divide it by the number. And that will give us our mean wind speed. So again, here's the other one where you can do a calculation. So we have wind speed in hours as denoted here and represented in this figure. Now we're going to go ahead and we're going to take our velocity and our number of hours. We don't have 0, right? Because 0 is not going to contribute anything, so we just leave it off. And we have number of hours times wind speed is 320. And then we do that for every wind speed until we get to the end. So the sum is 57,580. We divide that by the number of hours, and our mean speed is just over 6.5 meters per second, which this would probably be a reasonable location to consider putting up a wind turbine. Now, if it's 1,000 miles away from anything, it probably wouldn't be. So we have the mean wind speed, but if you've taken statistics, we have all these functions that will help us characterize what is the probability or likelihood, if you don't like probability, because I know some people when you say that term, they get a little nervous because it's a statistical term, but what is the probability of something occurring? Well, I can't use the normal density, probability density function, so let's look at a Weibull, which has this characteristic. So again, if you've taken statistics, depending on which statistics you took, you may have seen the calculus representation of it to figure out density functions. We won't do a ton of calculus here. We'll just do enough to make sure that we see it. But here is the Weibull distribution. And we're going to try it with a different number of scale values and shape parameters. So if you notice, my scale is constant, going to be 8, but my shape factor is going to vary from 1, 2, and 3. And out of the 3, which is the closest to looking like our realistic density function? If I look here, it looks like k equal 3 is pretty darn close to what it is. Not exact, but again, it's never going to be exact because we're doing it based on a modeling, right? So we're not going to get exact values. We're doing some rough modeling here. Now let's go ahead and let's tweak our value of k and adjust our value of c and see if we get any values. So in the previous one, we saw that having a k equal 3 looked pretty close. K equals 2 looks pretty close. But then when we start monkeying with the shape factor, we start to see how it gets pretty crazy when we adjust the shape factor. So if we use that value of k equal 2 here, that looks, and a reasonable shape factor, that looks pretty good. So let's come up with a new probability density function, and we're going to call it the Rayleigh distribution. That basically uses a Weibull and locks the k value, the shape parameter, at 2. And then we're just going to adjust our value of c, our shape parameter, trying to match the wind. So that's how we do wind resource estimations based on what the mapping data shows you in NREL. It's all based on using a Weibull distribution, k of 2, and then you adjust the shape parameter based on what you expect the average wind speed to be. So if you have an average, you can just adjust your function. Is your scale factor 4, 6, 8, etc., etc., etc. So I said we're going to try to limit the amount of calculus we need to do. And here's the thing where we actually have to do a little bit of it, because we're going to look at how we can solve for this value of c. So if we know what the average speed is at a particular location, we can use calculus to go ahead and solve for our scale factor by integrating our probability density function times the velocity, right? Because this is basically going to give us the average for a particular location. Here is our Rayleigh probability density function, right, with a specific value of k equal to 2. So if you go back a couple slides and you take a look, this is just with a value of k equal to 2. And now we're going to substitute that into here, and we're going to integrate what that value is. And if we do our integration, we're going to end up with approximately, pretty close to a c that's approximately 0.886 times c. All right? So the reason why we do that is we don't want to write things in terms of a scale factor, because that is not something that you're going to find on any map. But if you go to NREL's website, you can get an average wind velocity, which is here. So to figure out what the probability of any specific velocity is going to be, you're just going to plug in your average wind speed, the v bar, into this equation. So that's a fixed value. Then if you want to know what it is at 5 meters per second, 7 meters per second, et cetera, you're going to update your value of v to figure out what the actual probability that is going to be. All right? And it's not based on k or c, it's based on average value. And it's using the exact, so that's what that pi, square root of pi over 2 is. Okay? So that's how we can go ahead and actually calculate, what the wind speed is, because we want to predict how much power is going to be out of a machine and whether we can make a project viable. So if we know the average speed and we know the probability density function, we can calculate the velocity. Then we can look at the turbine manufacturer characteristics, and they'll give you a curve that says at 7 meters per second, here's what the expected power is. At 8 meters per second, here's what the expected power, on and on and on. Then once you know the number of hours per year at a specific wind speed, you can calculate how many kilowatt or megawatt hours you're going to produce. And then you can multiply that by what you expect to be able to charge, or you can do your calculations and figure out what you need to be able to charge to break even and pay off your plant. So the engineering economics that we did in a few lectures, you can actually do that based on calculating how much energy we can produce. So essentially what I'm saying is you can calculate what your expected capacity factor is going to be for a wind farm, okay? So a wind farm that is designed to put out 10 megawatts, you can calculate what you expect the capacity factor is going to be. Once you have that capacity factor, then you can calculate how many megawatt hours you're going to produce, and then you can take your costs, your fixed costs, and your variable costs, add those together, and then you can figure out what you need to charge for a kilowatt hour, and then can you make money or not. Very simple calculation, not very simple, straightforward calculation, but that's how you would go ahead and come up with some cost estimates, because you got to be able to pay your plant back. So now we'll talk a little bit about how we actually get power out of the wind. So easiest way to do it is we have a wind turbine here that has a wind swept area from the top of the blade to the bottom of the blade, and we're just going to replace that with a cylinder that has the dimensions of that. So we have the volume of air moving through the cylinder as the area times the length. The mass of the cylinder, we're just going to multiply by the density of the air, which is pretty much fixed, although it does adjust a little bit based on temperature. And then we're going to do a kinetic energy calculation using 1/2 mv squared. You probably remember that from physics. It's just 1/2 mv squared. So the mass that we need is from this equation, and then we can substitute that into here. So 1/2 rho density times the area times the length of the cylinder times the square of the velocity. Well, that's good, but we'd like to do it in terms of a mass flow rate. So we don't care so much about the length. We're looking at things with respect to flow, mass flow, because again, that, the cylinder is endless essentially, hopefully. The wind is always going to be there. So we're going to be looking at a change in mass over this change in length. So that's rho A velocity times delta T. And we can solve that for the change in mass over the change in time is rho air times the velocity. Then we can actually get the change in energy, which is 1/2 change in the mass times the velocity squared. And we're going to move out our delta T by the substitution here. Whoops. And now we have the change in energy with respect to time is equal to 1/2 rho A V times V squared. The change in energy, if you remember our units for energy, it's a joule, and delta T is a second. A joule per second is defined as a watt. So that is the power that is in the wind. How much power is in the wind is 1/2 rho A times the cube of the velocity. Remember how I said power in the wind is not linear, but is nonlinear? You can see it's based on the cubic of the velocity, not just the velocity term. So that's just kind of substituting. We always use the upstream, the undisturbed wind, because if we use the downstream wind, that's going to depend upon how much power you're extracting, so it's a very difficult one to take into account. So we'll just use the upstream wind speed for that. This is the area, which is the wind-swept area, which essentially is pi r squared, right? So take the diameter of the blades, divide it by 2, or if it's the blade, if it's 80-meter blades, each blade itself is 80 meters, you can just use the value there. But that's all you're doing is just pi r squared to get that area. And then you get power, which is in watts. So let's take a look at what the question.
Does changing the number of turbine or like the area, like the number of blades on a turbine, it seems like it wouldn't change anything in that equation. Does it change like the efficiency?
Very good question. So adding or decreasing, because you can go down, right? Because we're typically seeing 3. Increasing or decreasing the number of blades does affect efficiency, but it's not a one-for-one relationship. A lot of it has to do with something called the tip speed ratio, and so we'll look at that in the next lecture, I believe, where we actually cover tip speed ratio. But there are some applications with very high wind speeds. It's better to go with double blades or single blades. Anything more than 3 blades tends to be for low-speed applications. So if you're, running a mill or something like that, and you got, in the middle of Texas with really low wind speeds, you need a lot of blades to be able to do it. So that would be a case where you would want to look more at that. So we'll talk more about that when we look at tip speed ratio, but that will be more in the next video. But that's a very good question. Great question. So we want to figure out what the average power is in the wind, and we want to do a power density. Not a power, but a power density, because it's usually better to do it in terms of how many watts per meter squared. So if I have 12 meters per second wind, my air density is 1.225, which is the standard that you'll use. So if you don't know what to use, just go 1.225 kilograms per cubic meter, and that will generally be accurate. And if we want to figure out what the power density is, we just plug it into here. We're going to divide by our area to make sure it's in watts per meter square, and we end up with 1,058 watts per meter square, average power in the wind. And so you can go back and look at those tables and you can compare, but keep in mind we have to be careful that those tables are looking at some other values. I think it was, 12.9 was 2,000. I think it was 12.9 was 2,000 watts per meter squared, and so you can see it goes up pretty quickly. So that's the cubic of velocity, right? So you can sort of follow along and how you see how the wind speed is a big impact on the amount of power in the wind. Not as obvious, but remember how I said 6 meters per second you want to be at least in the ballpark? Well, that's only because you only get about 100 watts per square meter at 6 meters per second. Whereas if I double the speed, I more than double the power, right? I go up to 1,100 almost watts per meter squared. So locating in a site that has a much higher average wind speed makes a huge difference in the economics. So going from 6 to 7 is a big, big change. And so finding all those good wind resources is a way to go. And that's why offshore wind is such a wonderful opportunity, because there is a lot of power in the wind. It's just very expensive at this point, so the economics don't necessarily play out at this point. So I think this is a pretty interesting one too. The energy in 1 hour of 20-mile-an-hour winds is the same as 8 hours in 10-mile-an-hour, right? So it's by a factor of 8. Okay, double the wind by a factor of 8, because it's the cube, right, of the velocity. So 2 cubed is 8. So here's another example for comparison purposes. We want to compare 50 hours at 3 meters per second, 50 hours at 9 meters per second. My average wind speed, right, 50 at 3 and 50 at 9 would be 6. And then compare that to 100 hours at 6 meters per second. Which one do you think would have more power? Would it be the first or the second? They both have 6 meters per second, or would they be the same? Well, if it was a linear one, it would be the same. But because it's the cubic of the velocity, we're going to see how this one has a huge change. So let's look at the one where we have 6 meters per second for 100 hours. We're going to get about 13 kilowatt hours per square meter with 100 hours at 6 meters. I do the same thing for 50 at 3 and 50 at 9, and I get nothing. At 3 meters per second, I'm getting 22 at 50 hours at 9 meters per second. So adding those together, I'm getting 23.2, which is 10 kilowatt hours more, even though the wind speed average is the same. So you have to be careful when I say average wind speed. That only tells you part of the story, right? So that's when we need that probability density function to help us get a better, more accurate representation of that. So the last thing we're going to do is we're not going to use just that mean per se of the wind. We're going to actually use this cubic to get a better representation. So I'm going to look at things in terms of average power in the wind, and I'm going to look at the cubic of V cubed, not V, but V cubed. So now I'm going to take the cubic of V average, stuff that into my probability density function and integrate it. Now I'm going to use my Rayleigh distribution with my average speed approximated by square root of pi over 2 times c. This is my original function. Whoops, let me move up a little more. That I had. And then I'm going to substitute that into here. And what I end up with is 3/4 c cubed times the square root of pi. When do I use that? Well, because that's going to allow me to recalculate a better shape parameter. But more importantly, what I'm going to use that for is this is way more important to calculating power than V average. So what I'm going to do is I'm going to modify my average power in the wind equation to look at this, which is I take the average of the power and I multiply that by 6 over pi. All right? That's a big difference comparing. It's not just the cube of the average. It's actually multiplying it by 6 over pi. So then I can plug that in there, and I modify my equation based on average wind speed. So that's 6 meters per second or 7 meters per second. If it follows our Rayleigh probability density function, right, based on the average wind speed, which most of the time that's what we're going to use is the Rayleigh probability, we're going to use this equation here. And if we need to get average power in the wind per meter squared, we'll just divide the A by both sides. Okay? So obviously it's 6 over, so it's 3 over pi times rho times the cube of the average velocity. And that is the equation that would have taken into account. So if you take a look at the 50 meters per second at 3 and the 50 meters per second at 9 and use the average there, you would have gotten the correct results. Okay? This shows you, though, by assuming Rayleigh distribution is a dangerous thing. Altamont Pass is near Palm Springs in California. So you can see Rayleigh is here. This is actual data. They don't look the same, do they? So, you know, if you're going to put up a wind turbine, you know, a Pika Energy wind turbine that, you know, maybe installed cost is $8,000, okay, you know, you're not going to spend a ton of time analyzing the data. But if you're going to put up, you know, 33 megawatt turbines, it's going to cost you, you know, tens or 20s or maybe more millions of dollars, $50 million. You're not going to do that just based on some typical values. So if it's $1 million or less, you might be willing to take a risk. And so that's what some of the community's wind turbines projects have been doing, is to figure out how do we make this work just by mapping data. So that was really popular 10 or 15 years ago, where you saw people just go approach schools and say, I'll sell you power at a discount, and then they can still make money. So they were selling it cheaper than the 18 cents a kilowatt hour the utilities were doing, and they were making money. Now, you don't see that much anymore because all the good wind resource areas have pretty much been taken. Same thing with hydro, right? You don't see a lot of hydro construction happening because of that. So average power in the wind, we have 50 meters with the wind speed is, let me back up. We want to estimate what the power is at 50 meters given 10 meter wind speed average at 6 meters per second. We know what the roughness coefficient is. Alpha is 1/7. We're going to use standard density of wind or air. So the first thing we need to do is correct this 6 meters per second at 10 meters to whatever the wind speed is at 50. So we just substitute in here to get V50, and our average is 7.55 meters per second. Again, assuming Rayleigh statistics with a roughness coefficient of 1/7. Now we're going to do the average power, and we're going to plug it into our previous equation that we derived, and we're going to end up with 504 watts per meter squared. So this would probably be a pretty viable site to consider. And I think that's my last slide. That's my last slide. So thank you very much. I hope you enjoyed this first lecture. We have 2 more lectures on wind. The next one we'll start to get into some of the more details of turbines and how they extract power, and then the one after that we'll have to start looking at the negatives of wind to consider. So thank you and have a great day.